So this is to help you wrap your brain around how we can use cosmic potential energy. First of all, suppose a mass little m is moved from the surface of a planet to a distance big R from the center of the planet. Which of the following is true about the work done? The work is given by that. The work is given. Which of those looks like it's the correct equation for work? Well, looking at my formula sheet, one of my options for work is this one, force times distance. I guess if I modify it for this specific situation, it would be the force of gravity. Why can't I use that here? Sorry? The force of gravity is changing, so we can cross out A. We can cross out B. I think B is trying to sneak a bit of an R minus R. I think it's trying to sneak a change in. In fact, what's our best definition of work? Unfortunately, the ugliest and most cumbersome, but what's the one that we can use kind of anywhere? The work energy theorem. All right. Work equals the change in potential plus the change in kinetic. I phrased this very carefully. I said a mass little m is moved. What I was really trying to suggest to you is it starts at rest and ends at rest. Some invisible angel or big hand is just moving it in the middle there. But my point is none of that. What's change in anything? So this is how you calculate how much rocket fuel just to get the rocket to the right height to stay in orbit. Will it stay in orbit if we just do this? Alicia, you're right. You're right. Did you do a little head shake there? Now you're doing a nod. No, okay. Why won't it? Because to stay in orbit, it's not just, but is there gravity there still, Spencer? Yes, there is. What do we have to do? We would also have to give it the right kinetic energy to give it the right orbital velocity. But for now, we're just looking at getting it there. What's changing anything, people? So this is going to be negative big G, big M, little m over, I guess our final in this question is big R. Minus negative big G, big M, little m all over, and I guess our initial is little r. Do you see that in C or D or E? Why can't I do C? Why can't I factor out the big G, the big M, and the little m and just have R plus R? Well, first of all, I guess a minus minus would make it a, you know what? It would be negative big R plus little r, but also where are the r's here on the, okay, well, here's what that means. Unfortunately, when you're adding or subtracting fractions, you have to have a common denominator. Are those two numbers the same? You can't combine them conveniently. Trust me, if there was a shorter, better way to write this, I would have introduced it to you. Trust me. So unfortunately, no or no. I had somebody the other day, Mr. Dewick, why can't I factor some of this out? And I showed them, you know what? You're going to do, there is one way to write this kind of factored. Sorry, I crossed out the wrong one. I crossed out C, meant to be D. There is one way to write that factored. If you really wanted to factor it out, it would look like this. You could factor out the big G, the big M, and the little m, and you would have negative 1 over big R plus 1 over little r. That works. That's not significantly less typing, especially if you're going to backspace and edit like I've taught you, than just doing it this way. So I've never bothered teaching that. Explain your answer. I think we derived it right here. Okay? So that's how much work, how much rocket fuel you would need just to get it up there. And when we did it for Earth, we found it was typically in the 10 to the 10th range, maybe 10 to the 9th if you're not going very high, or 10 to the 11th if you're going really, really high. It's typically less around the moon. I showed you a video the other day of why we should build bases on the moon. Launching from the moon makes way more sense. Let's talk about escape velocity. Should technically be called escape speed because it's a scalar, but they say escape velocity, so I'll use the jargon. What is escape velocity? To escape from a planet's gravity well means, in theory, to travel an infinite distance from the planet. That's the theory. In reality, it means you get so far away that gravity is basically negligible. The pull of gravity has become so small that you can ignore it. And what we're going to do is we're going to barely escape. We're going to ask, how fast would you need to leave the Earth so that you could shut your engines off and coast all the way to the edge of the universe, but time it so well that right when you reach the edge of the universe, you also came to a stop. No extra energy. Okay? So that when we're talking about escape velocity, we're asking, okay, what do you need to get out of Earth's gravity well, get to the edge of the universe, but not have anything left? Oh, and if you go faster than that, hey, you'll have some extra energy left. Really, what escape velocity asks is how much kinetic energy is required to bring potential energy to zero? Because where is potential energy zero? All the way out at? Got the argument? And we can solve for it by using conservation of energy. It's going to look like this. Let's write our first line right here. KE initial plus PE initial equals KE final plus PE final. And then who remembers what I usually asked after I wrote this out? I usually said, are any of these zero? Where do we want to end up? All the way out at? It's strange, but that's zero. Out at infinity. And we want to time this so well that when we get to infinity, how fast are we traveling? That doesn't mean that there's nothing there. It means the right-hand side actually works out to what number, everybody? Zero. So we get this. A half mv initial squared plus negative big G, big M, little m over r initial equals zero. Kinda strange. You know what? I think I would plus this over to the zero side. It will make it a prettier equation. If I do that, I get a half m v initial squared equals positive big G, big M, little m over r initial. Oh, huh. Is escape velocity different for the Starship Enterprise versus a smaller space shuttle versus a tiny CubeSat? Turns out, doesn't matter how big your spaceship is. Let's get this V initial is our escape velocity, how fast we need to leave. Let's get the V by itself. How? Times by 2 and then? Yep. Escape speed, should be called escape speed, but we'll call it escape velocity, is the square root of 2 big G, big M over R. R initial, how far you're starting from the center of the planet. What was V orb? Don't write this down. It turns out escape velocity is only root 2 as big as to get in orbit. This is why. To get in orbit is really tough. We had to do escape velocity to get to the moon. That wasn't the tough part. The tough part was getting all that equipment into orbit first. Yeah, and go a little faster and suddenly you're at escape velocity. In fact, you know what? Let's find escape velocity for the Earth and for the moon. Let's go like this. So escape velocity for the Earth is going to be the square root of 2 big G, big M over R. You don't need to memorize this. I've showed you the derivation. I mean, if you want to add this to your blue sheet, you can. I don't think deliberately I did not put it on your yellow sheet. There is going to be an escape velocity question on your test. Although for giggles, Rachel, we're going to do it around a black hole because why not? What is escape velocity of the Earth? It's going to be 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, divided by, and if we start on the surface of the Earth, it will be 6.38 times 10 to the... By the way, what if we were further away from the surface of the Earth already in orbit? What would escape velocity be? That smaller, which is why once you're up there, it's easier to get away. What do you get? Sorry? Yeah, I know it's a little over 11 kilometers a second, right? Can we do that? Yes, the Apollo rockets did that to get to the moon. They left Earth's gravity well, coasted, and then got pulled into the moon's gravity well and ended up in orbit there. And then reversed the procedure to get back. If we ever go to Mars, that'll be part of our procedure as well. We'll go fast enough to leave Earth's gravity well, coast, and then get sucked into Mars's gravity well. Probably, if we're clever, we'll try and come up with some kind of a slingshot arrangement, hopefully, and then work our way back. But getting home from Mars, once we're in orbit around Mars, won't be the big challenge. Leaving Mars will be the big challenge. Landing on Mars will be the bigger challenge. What? Yeah.
So we'll have to derive this equation on a test.
Sorry?
We'll have to derive this equation on a test.
You'll have to derive this on a test, or I have a few kids who commit it to memory. If you do, fine, but I'm going to ask you an escape speed / velocity. I wish they called it speed. Anyways, on the test. Let's do the moon. It's going to be the square root of 2 big G, big M, over R. I will, by the way, in case you're worried, later on, either this lesson or tomorrow's lesson, I will redo the derivation a few times so you have the practice, so you can decide whether you want to just memorize this or realize what we're really saying is conservation of energy, but both finals equal 0. I have not memorized these numbers. 2, I know the 6.67 times 10 to the negative 11. I have no idea. What's the mass of the moon? It's 7 something. Times 10 to the 7.35 times 10 to the 22. Radius of the moon? What do you get? Again, all of you should practice typing this and make sure you can get the answer, since you're going to see this in the future. I know it's less than Earth's. I think it's significantly less than Earth's. We watched a video yesterday where astronaut Don Pettit said, look, the best thing we can do, build a permanent moon base, launch things to the rest of the solar system from the moon. Then we can get our payload package fuel ratio down to about what a jet is. Yeah?
Is it 2,374?
2374? Significantly less. Right? Basically 4 times less. Sorry?
9,000 kilometers now.
Oh, you could, I was going to say, and I thought I was still in seconds. It's 2.3 kilometers per second. Yeah. This also means that meteoroids and asteroids will impact a planet with at least this escape velocity, because whatever they've left, they're going to gain back all of this kinetic energy as they lose all of that potential energy. Oh, and if they didn't start at speed 0, they'll have even more kinetic energy. Of course, it's possible to reach infinity and still be moving. That particular equation would look like this. KE initial plus PE initial equals KE final plus PE final. We would still be out at infinity, so that would be 0. But, no, you still got some motion to spare? Okay, that would look like a half m v initial squared plus negative big G, big M, little m over R initial equals a half little m v final squared. The little m's would still cancel. And then you can kind of mix and match from there. Example 3. Let's look at a little bit black holes. We'll do a whole lesson next class on black holes because they're very attractive. Nothing? They're very gravity joke? Okay. A spaceship is 8.5 times 10 to the 9th meters from the center of a black hole. The black hole has a mass of 50 times that of the sun. What's the gravitational field strength? I like question A. I like question A. I like question A. Question A is a nice question. What do I mean by gravitational field strength? First of all, did I say find the gravitational force? What did I say? Find the gravitational field. What's that? That's little g, and there is an equation for little g on your formula sheet. Spot it. That's not on your formula sheet. Is there? I don't think it is. No, so don't say F. There's an equation for little g on your formula sheet, is there not?
Oh, Fg over M.
Okay. Gravitational field strength is that. Look up. In Physics 11, don't write this down. We could use little mg for gravity because we were always on the... Are we on the Earth? So what's the cosmic gravitational force equation? What's Fg, the universal one? Big G, big M, little m over R squared. Oh! I guess they didn't need to give me the mass of the spaceship. That's good. This is the equation. We started out in lesson 1 with this equation. This is the equation for gravitational field strength anywhere in the universe. If you plug in 5.98 times 10 to the 24th and the radius of the Earth, you'll get 9.8. But we're around a black hole. Am I expecting a gravitational field strength bigger or smaller than 9.8 around a black hole? Probably going to get a fairly big one. Okay. 6.67 times 10 to the negative 11. What's the mass of the black hole? So it's going to be 50 times... the sun's on your sheet. I have no idea what it is. 1.98 times 10 to the 30. Okay. All over. By the way, you'll notice this one has an R squared in the bottom. Escape velocity has an R in the bottom. Potential energy has an R in the bottom. Force has an R squared. Be really careful whether it's an R or an R squared. Just really pay attention is all I can say. This is going to be, what was the radius? 8.5 times 10 to the 9th. Don't forget the squared. What's the gravitational field strength here? Sorry? 91 newtons per kilogram. Anybody else? Roughly, very roughly, 9 Gs. How's that going to affect these astronauts? Sorry? Not at all. Not if they're in orbit. Will they feel it at all if they're in orbit? They're in free fall. Getting in would be a challenge because then they would feel it because they weren't in free fall. Getting out would be a challenge. But while they were there, it would be like on the International Space Station. The only issue might be that such a big gravitational field, there might be a difference in the gravitational field at the ceiling of their spaceship versus the floor, and it might be, you could feel it. Maybe not. But yeah.
How are we getting the newtons per kilogram?
Great question. Spencer said, how are we getting newtons per kilogram? Ready? What was the equation for little g? Right from your formula sheet. Read it.
Would be big G.
No. What I read it. There's an equation that says, people, there's an equation on your formula sheet that says little g equals.
FG over F.
Oh, sorry. What's F measured in? What's force measured in? What's mass measured in?
Kilogram.
That's how we're getting newtons per kilogram.
Okay.
It also is meters per second squared because it's an acceleration.
So.
Is it 91, folks? Maybe he's wrong. Yeah. Okay.
I got the wrong answer.
Yeah. So double check the squared. First thing.
Yeah.
Sorry?
Yeah, that's it.
Okay, double check the squared. Okay, let me pause. B. How fast would the spaceship need to travel in order to escape from the black hole's gravity well? I like question B, I like question B, I like question B. Question B is a nice question. What's this asking me to find? Let's do the full derivation. Now, if you memorize it and you can go straight, great. But let's do the full derivation for practice. So what did we say? We solved this with conservation of energy, G. We start out by saying KE initial plus PE initial equals what? Strangely, 0. We want our final out at infinity. So that's going to be 0 for potential energy. And we want to come to a stop right when we do that. That's going to be 0 for kinetic energy. So we're going to get a half little m v, and this is escape squared, plus negative big G, big M, little m over r equals 0. Now what did I do? Yeah, I get rid of that negative. I got a 0 there, I got a negative. Let's plus it over. And I end up with a half mv squared equals big G, big M, little m over r. You know what? Look up for a second. Here's what we're really saying. To escape from a planet, all of your kinetic energy has to be turned into the potential energy required to get to 0. Infinity. So that kind of makes sense. They didn't need to tell me the mass of the spaceship. Get the V by itself, times by 2, or yes, Owen, divide by 0.5, but I would times by 2 here, square root. I'm guessing it's going to be bigger than 11,200. It's going to be bigger than Earth's because the gravitational field strength is much stronger here. So it's going to be 6.67 times 10. Mr. Duick, yes. Instead of writing out 6.67 times 10 to the negative 11 every time, can I just leave it as big G? I think now that we've talked about it long enough, I'm okay with that. I never allow kids to do that at the beginning because they start to think big G is 9.8. Why would that I don't know, but they do. Mass of the black hole was 50 times the sun, 1.98 times 10 to the 30th. All over. Hey, you know what? I'll bet you, stop typing, you could probably backspace, delete the squared, times by 2, and square root answer button. That should work. Did any of you notice that? Because I'm noticing it's basically the same numbers. You don't have to, but if you're lazy like me, you absolutely would have gone, wait a minute, I can just backspace, delete the squared, hit equals, times by 2, hit equals square root. Answer button. You're going to get an answer bigger than 11,200.
I feel like 1,246,863 might be a bit off.
Is it 1,200,000? Or is that off? I mean, it's a black hole. You could get a really big answer.
I'm looking for numbers. So.
I'm clearly going to have to type this in for all of you. I know I've forgotten the 2. So for the gravitational field, I would have done that, and there's where I got the 91.4. And then I would have said, oh, cool, for escape velocity, I can just delete the squared, insert a 2 times. In fact, if I'm really lazy, insert a square root, close off the bracket, and I get 1246482.
Yeah, it's right.
Yeah.
My things are off with the D's.
Oh yeah, yeah. You're using it. So 1.25 times 10. 1, 2, 3, 4, 5, 6. C. How far away from the black hole is the event horizon? What's meant by the event horizon? That's the point of no return. If you go past that spot, escape velocity is faster than light, which means you're out of luck. Nothing in the universe is coming back from that location. And it's really neat. We can actually start with our escape velocity equation. Write that down. And here's what we're going to do. Going to get the r by itself. How would I get rid of a square root? Square that. Square that. That's going to give me v squared equals 2 big G big M over R. Stuff moves diagonally. And then what we're going to do, we're going to let V equal C. Who remembers from Physics 11 what was lowercase c? If we let escape velocity be the speed of light, that tells us the black hole's event horizon. It tells us where this black hole starts becoming what we think of as a black hole. So it's going to be 2, 6.67 times 10 to the negative 11, 50 times the mass of the sun. What is the speed of light? How did you know that? Did you remember it, or did I give it to you on your formula sheet? And are you clever enough to look at the data section of your formula sheet? Okay. Speed of light is 3 times 10 to the 8th. Hey. You know what I did? I went backspace on my calculator and I said, wait a minute. I just delete the square root, but I've got the 2. I've got the 6.67, I've got the 50, I've got the 1.98. You know what? I just need to delete by 3 wrong button. Scientific notation button, 8. I think that's good. No squared, no nothing. And I get 4.42 times 10, 4.40 times 10 to the 13th? Or am I wrong? Anybody else? Yeah? Yeah.
Is there a constant for the speed of light? Because I see C0, C1, and C2.
On the formula sheet?
On the like calculator.
Oh, on the formula sheet, yeah, it's 3 times 10 to the 8th. That's actually not quite right. It's 2.998 something. It's actually one of the few constants that is defined because we've defined our definition of the second based on how far light travels in 1 second, and because those two define each other, those won't change.
I'm just wondering if it's like on here.
Oh, it's on there?
C1.
I think neither. I think C. I'm sorry. There is a squared. I'm sorry. Someone said squared, and I went, no, you're right. It is C squared. I'm terrible, Mr. Dewick. Do I leave it on YouTube just to show that I'm fallible? I will. Sorry, that's way better. You get 146. Is that right? 146740 meters. Or divide by 1,000. We would say this black hole had a radius of about 146 kilometers. 147. Okay? So its diameter would be what? About 300 meters? Sorry, 300 kilometers? So about from Vancouver to Kelowna? But you've got packed into that distance 50 times the mass of the sun. Very dense. That's what makes black holes black holes. It's not their mass, it's their density. It's how small an area you cram their mass into. Yes? Spence?
The speed of light 2997.
Yep, times 10 to the 8.
So it's C0.
There you go.
It is C1.
Example 4. I like example 4. I like example 4. I like example 4. Example 4 is a nice question. Whew. This here is probably the longest question of the year. First of all, no, Liz, this is rocket science. You went, oh, no, this is, I get to do rocket science. Liz, what's this question asking me to find? Keep reading. Stable orbit, so not the work just to lift it up, but the work required to put it into a stable orbit. In other words, we're going to go work equals change in potential plus change in kinetic, and none of these are going to cancel. Not only that, I would say, nice try, Mr. Dewick, with the 25,500 kilometers. 25,500, I would multiply that by 1,000, and I would say, oh, that's 2.55 times 10 to the 1, 2, 3, 4, 5, 6, 7. That distance there, is that a radius or an altitude? How do you know? Okay, so I'm not going to have to add the radius of the Earth to it at least. So, yay. Liz, what do you want to find first? Change in potential or change in kinetic? Okay, what's change in anything? And it's weird how that's tough to say, but it is. You're not the first student and you won't be the last one. It's going to be negative big G, big M, little m over our final minus negative big G, big M, little m over our initial. It's going to be negative 6.67 times 10 to the negative 11. You know what? Big G. As long as you know that that's not 9.8. What's big M? Are we Earth?
Yeah.
Okay. 5.98 times 10 to the 24th. What's little m? I scrolled down. Sorry?
12,005.
Okay. Divided by, and our final was 2.55 times 10 to the 7th plus same thing times same thing times same thing divided by, and we're starting on the Earth, 6.38 times 10 to the 6th. I'm going to do the first term. I'm going to write it down to like 5 sig figs. Then I'll do the second expression by backspacing and editing. Write that down to like 5 sig figs, and then I'll combine them. You can try this on your own. I'll do it up here. $1.9552. Yeah, and Spencer, you're using the constant. You should match me probably the first 3 sig figs, maybe the 4th sig fig, but I don't know.
Match the first 2 and then...
Okay. And then you'll be within 1 probably on the 3rd one, plus or minus. You'll either have a 6 or a 4 there.
Yeah, 6.
Yeah, I'm good with that.
Also, I just used my answer and pre-answer button. No, pre-answer button.
Oh, you got a pre-answer button.
Yes.
Well, nice. So he's got 2 answer buttons on his. That's a bonus.
Yeah, one for the early one. Yeah, I can use this.
What do you have? Casio?
Yeah, Casio, whatever it is.
What model?
Same one as him, same one as Parker.
So some of you might want to look, if you have a Casio, you might have a pre-answer button, which would be really nice.
Yeah, it's like on the answer on Alpha.
Sorry, it's what?
Alpha button.
Alpha and then answer button?
Yeah.
Oh, okay. There you go. I got 5.8596 times 10 to the 11th joules. And that's, I said to you, yeah, it seems right, 10 to the 11th-ish area. Liz, are we done? No, even close. Alicia, what else do we have to find? Not just the change in potential, but the change in? What's changing anything, Alicia? So it's going to be a half mv final squared minus a half mv initial squared. Now, Alicia, we did say we're going to launch from the North Pole. So initial is 0. Who knew that Santa had a rocketry program? Of course he does. How do you think he delivers the presents so fast? By the way, v final, that's the orbital speed, right? Alicia, read the question. Did they give me the orbital speed? See, the previous ones of these that we've done, I gave you v orb. Did I here? Did I give you it here? Are we in orbit? Gravity is what's pulling me in a circle. I can find the orbital speed. Big G, big M, little m over r squared equals m. And since I want speed, I'll use the v squared over r. Hey, little m cancels. Hey, one of the r's cancels. I was going to square root, but then I went, wait a minute. Don't I have a v squared sitting right here? I'll just leave it as v squared because I'm that lazy. I'm going to take this whole mess, and what I'll get, it turns out, I guess, is that the change in kinetic energy is a half little m big G big M over R. Wait. If I can bring back a few lines, like say this one, I've got most of this typed in already. There's big G, there's big M, there's little m. I guess I just need to times by a half or divide by 2. And I need to change R final back to the 2.55. So if you know how to go back multiple lines on your calculator, really handy. Way less typing. If you have a cheap, crappy calculator, hopefully by now you've converted to a better calculator. I get 9.7761 times 10 to the 10th. Is that right? Now, I'm seeing about 5 or 6 of you, not mentioning any names, who aren't bothering to try typing this in. This is really difficult to type into your calculator, and you should probably be practicing typing this into your calculator to make sure you can get the right answers, because it would be silly if on the test you couldn't get the right answers even though you had all the wrong work because you hadn't practiced typing this into your calculator during class. Yeah.
What is little m here?
Satellite. Little m's always the satellite.
Okay, so the big M is the
Earth. Big M is the planet causing... Big M is what's creating the gravity. Little m is what's experiencing the gravity.
Oh, I already have it in just because of the way that the equation is. It's little
It's right there.
M, and I have GM little m. So
Yeah.
just, if there's
Multiplying order doesn't matter.
yeah, if there's a half in front, can I just put 2 on top, or the bottom?
If there's a half in front, you can put a 2 on the bottom or a 0.5 on top. You divide by 2. 9.7761.
And that's for the United.
Work is going to be both of those added together. 5.8596 times 10 to the 11th plus 9.7761 times 10 to the 10th. 5.8596 times 10 to the 11th plus, answer button. And I get 6.84 times 10 to the 11th.
I also
Yeah, I figured so. Usually, with the amount of rounding off I've done as well, we'll probably match on at least the second sig fig, probably the third. Or you'll have a 3 or a 5 where the 4 is.
we usually always match the first 2, and
Yep.
the third's either one off.
Yep. So that's about as long as a question I can ask you. I would feel comfortable doing this on a quiz. On the test, I will ask you how much work to put something in orbit, but I'll give you the orbital speed in the question. In other words, I'll have done this step and crunched it for you, and I'll tuck that up there for you. Okay? So I will. But otherwise, is that a lot of energy? Takes a lot of rocket fuel to get stuff in orbit. This is why orbit is so expensive. Example 5, you can make a little note if you want to. This is a handy error check. You can survive just fine without this. I will not ask you this, but there's a couple of neat patterns. It turns out, if you're in a circular orbit, the kinetic energy is half of the potential energy, but positive. The total energy, kinetic plus potential, ends up being just half of the potential. And the total orbit energy is the opposite of the kinetic. Say, what? It says, use the expression for orbit speed. So there's orbital speed. Actually, I'm going to write it as v squared equals big G, big M over R. I squared both sides. Annika, what does part 1 want me to prove? We're example 5 right now. The what? Stop. What's our equation for kinetic energy? That hasn't changed. What's the equation for kinetic energy? Okay, so I'm going to write this. Ke equals a half mv squared. But now I'm going to plug orbital speed squared into here. And I'm going to get a half little m big G big M over R. And if I just tidy this up a little bit, I'll get a half big G big M little m over R. What's this? But positive. Okay? This is 1/2 of potential energy, but positive. I'll put absolute value signs around it. That's a terrible absolute value sign. It turns out the kinetic energy is half the magnitude of the potential energy. Why is that handy? Well, you know what? If I ever find the kinetic energy in orbit, and I happen to know the potential energy up there, I might quickly go times by 2, and if they're the same number, I know I did them both right. You can survive just fine without it, but it's kind of a neat pattern. Kiana, what's the second thing you want me to show? Total orbit. So total energy would be potential plus kinetic. So it would be negative big G big M little m over R plus a half big G big M little m over R. I'm using the expression for kinetic that we just found on the previous line. What number is sitting in front of the big G technically right there? This is -1 plus a half, because they are like terms. They all have a big G, a big M, a little m, and an R. What's -1 plus a half? I get -1/2 big G, big M, little m over R. Kiana, can you read to me statement 2 again? What we're trying to prove? Can you read to me statement 2 again? Stop. There's the total energy. Is what? Keep going. Half of that. Yeah, it is. Again, can you survive just fine without that? Yes. But could you use this as an error check if you wanted to see if you'd done something right? Sure. Or if you found the total energy and you also have found the potential energy, you know, oh, it's half as big. Or you know what? Wait a minute. This was half as big but positive. This was half as big but negative. Huh. Rachel, read to me statement 3. Stop. This is... Are they the same, but one's negative, one's positive? Yeah. So that was, I mean, I can't exactly call that nerd trivia. It's kind of neat. Do you need to memorize it? No. But every once in a while, I've noticed as I've been solving a question, oh, the kinetic energy and the total energy are the same. I probably did this right. Oh, except the total energy's got a negative sign in front of it, but same magnitude. Okay. Looking at the clock and seeing I'm probably going to need to go a little bit into tomorrow as well. But so here are all the different ways that I can throw either work or conservation of energy, GG, at you. So example A says this. A rocket at rest, I would probably underline the word at rest, on the surface of the Earth blasts off from rest and rises to a maximum altitude height h to a maximum distance r. Write equations to calculate the what? Work equals change in potential but Kessler, what does it want us to assume? Read the whole thing. Assume the... There's a word, the sentence says... Okay? What's changing anything? That's how much work required just to lift something up into space. And then in all caps and underlined, I guess I should be shouting, this will not keep it in a stable orbit. Why? Okay? No KE. Okay? Here's another question I could ask you. So that would be, what could I ask you from this then? Probably I'd give you the final radius and how much work. What if instead I wanted to know how high? I would treat that probably as a conservation of energy, because there is a change in height, change in speed, and a yucky curvy force. A rocket moving at a speed v at liftoff, so that's vi, rises to a height h with no engine use. It coasts. Write an equation to calculate the maximum height using conservation of energy, g. Assume the rocket ends at rest but doesn't start at rest. So conservation of energy would look like this. And the only one that I could cross out would be that one. This is going to end up being a half little m v initial squared plus, can I go mgh because I'm on the Earth? No, we're going cosmic, so we got to commit to it. Negative big G, big M, little m over r initial, and that's going to equal negative big G, big M, little m over r final. It is true that the little m's cancel. As far as I'm concerned, it would be fair game. The three variables here are v initial, r initial, and r final. I doubt I'd ask you the radius of the planet because it's going to be Earth or the moon, but I can give you v initial and say how high, or I can tell you how high and say how fast do we need to leave the Earth. For neither of these would I get the v or the r by itself. What I would actually do is, so if you wanted me to solve for v, I would move this to this side, get an answer, and then I would get the v by itself. Oh, you want me to solve for r final? I would get an answer, get a single number, and then stuff can move diagonally and I can get the r final by itself. But I would not try and get the r final by itself beforehand. A rocket moving at speed v at liftoff near the Earth's surface barely escapes Earth's gravity with no additional engine use. Write a conservation of energy equation that would allow us to solve for v. Note, we call this escape velocity. So what's our conservation of, well, it's conservation of energy. Except, what did we say was the weird thing? We wanted to end up at rest? And how much potential energy do we have out at infinity? Why? Because we won't fall. So we can't have any potential energy. So we ended up with this weird a half m v initial squared plus negative big G, big M, little m over r initial equals 0. We ended up with a half m v initial squared equals positive big G, big M, little m over r initial. Good, we're going to finish this. Don't turn the page yet. We haven't got the... So we ended up with V escape being the square root of 2 big G, big M over R. So there's the derivation, or you can remember it. I don't care. A rocket at rest on the Earth blasts off and enters a stable orbit. How much work will the engines do? Well, now that we're in orbit, it's going to be change in potential plus change in kinetic. Solve for change in potential. Solve for change in kinetic. And then add them. We just did one. That was that big, long question. So if you want to, you can write there, see example 4. And then I wrote here, this question is a lot of work. That's a pun, but also, no, it is a lot of work. What else could I do? A satellite is moving at speed v a distance r from Earth's center. It falls to the Earth. How fast will it hit the Earth? Is this question asking how much work? So how will I solve this? What's it wanting us to find? Speed. So how will I solve this? Are we in orbit? How do I know we're not in a stable orbit? Because we're crashing. It's not a stable orbit. How will I solve this? Ready? Is there a change in height? Is there a change in speed? Is there yucky curvy force? Everybody? How will I solve it? Okay? This is going to be, now the tricky part here is the initials are the space ones. It's really tempting to put the space ones in for the final, because usually we've been starting on the Earth and heading up. Here we're starting up high and heading down, but it's going to be a half m v initial squared plus negative big G, big M, little m over R initial equals a half m v final squared plus negative big G, big M, little m over R final. Don't pack up yet. There's still 45 seconds. As far as I'm concerned, there are 4 variables: V initial, R initial, V final, R final. Any one of those is fair game if I give you the other 3. But you will not try and get them by themselves first. You will get everything else to the other side, turn that into a single number, then get the thing by itself. If you want to get a head start on the homework, you can try number 1. Don't put your stuff away yet. You can skip 2. You can try number 3. You can try number 4. And I'll assign some more when I finish this lesson off tomorrow. Okay?